Okay. I'm really happy to introduce Andrew Bauman today. He's going to talk about some work he's been doing at Microsoft Research as part of our systems and networking seminar series, newly launched. I've actually known Andrew since for about 10 years.
Almost a decade.
Have spent a really pleasant summer in Zurich with Andrew at Monte Roscoe. But this is on completely different stuff from what he was working on then. Go ahead.
Thank you, Tom. Thanks for coming. So yes, this is a system called Komodo, and it's joint work with Andrew Ferriola, who was my intern a year and a half ago, and he's currently graduating student at Cornell. My colleague Chris Holbritzel and my former colleague Brian Parner, who's now at CMU. Unless you've been living under a rock, you've probably heard of SGX. SGX is an Intel hardware extension that gives you strong security for things called enclaves. And an enclave is effectively an isolated execution environment in which you can run some user mode code. And the hardware guarantees the confidentiality and the integrity of all the code and data inside the enclave and protects it even from more privileged code on the platform, like the operating system or the hypervisor, and from physical attacks, like people trying to read secrets out of memory. And the enclave is also backed by remote attestation, so it's a great feature for, say, secure computing in the cloud. If you want to do some computation in the cloud, you get an attestation that ultimately backs back to, in this case, Intel, that you know exactly what code is executing inside your enclave, and you can ensure that nobody else is tampering with that. So it's a fantastic feature, and lots of people are building systems on top of it. However, unless you've actually worked with SGX and built things with SGX, you may not realize quite how complicated it is. SGX1, which is the version of SGX that's currently available, adds 18 new instructions to the x86 instruction set. It also changes the way exceptions behave, changes rules for accessing memory. It interacts with almost everything else in the architecture. And SGX2, which is another extension that's on the way that adds some more functionality, adds another 8 instructions and more changes to the architecture. So it's a pretty complicated piece of hardware. To give you a sense of that complexity, Intel, in their architecture manuals, published this pseudocode, which is meant to be a sort of high-level description of what all the instructions in the instruction set do. This is one of the instructions in SGX. This is EADD. This is what you do when you want to add a new page to an enclave, when you're constructing an enclave. And if you can squint really small, you can see that it's doing things like checking a whole lot of security properties, checking flags, checking for concurrency, people trying to execute the same instruction in conflicting ways on different CPUs at the same time. It's doing things like copying a whole page worth of data around, updating internal data structures that are private to the CPU implementation of SGX. There's a lot of moving parts inside this one instruction. If that's not enough of an eye chart, this is E-init. I don't expect you to read this. I won't try to describe it. I'm just trying to give you a sense of this, a lot of complicated stuff that's being added to the x86 instruction set, the CPU implementation. And all of this complexity is in your what's called your trusted computing base, in the stuff that you trust when you run an enclave on top of SGX hardware. So it all has to be correct to give you the security guarantees that people want from SGX. So it's really complicated, and it shouldn't come as a surprise that it has bugs. The first acknowledged bug in SGX that compromised its security was last year. There's a microcode patch now to correct that. It's something complicated relating to the state of the processor at the start of day. Just giving you this as an example of course, when you try to build a system this complicated, even for hardware people, it's hard for them to get it right. SGX is also vulnerable to side channels, old and new. So if you want to build a secure system on top of SGX, you need to worry about things like, how does the execution of my code inside an enclave affect shared hardware resources like caches, TLB, branch predictor, speculation, as everybody's been excited about in the last few months. It also adds some new side channels of its own because SGX interacts with the operating system's paging mechanism. The operating system can get page faults from an enclave, can actually trigger page faults inside an enclave. So it can learn a lot of information about what code is doing inside an enclave in a very deterministic way by observing the trace of page faults coming out of an enclave. And there's some work in the security community that's shown that these so-called control channel attacks can leak a lot of, in theory, secret information out of the enclave just by observing those page faults. And finally, what really sort of got me started down this path is that despite, or perhaps because of its complexity, SGX is actually a fundamentally limited architecture extension. It assumes you're going to interact with it in certain ways and limits what you can do. To give you a slightly more concrete example of what I mean by this, look at how you manage memory inside an enclave versus how an operating system normally manages memory in the form of the virtual address space on a normal CPU. So traditionally, in the implementation of virtual memory, the hardware gave the software some kind of primitive mechanism to set up the hardware's virtual to physical translation the way that software wanted. So this would be something like a hardware-defined page table format. And the OS can construct any page table it wants, and in doing so, it can express basically any page granular virtual address space layout. It can do things like copy on write, it can do dynamic loading, it can do static loading, it can fiddle with permissions on the fly. The OS has basically full control over how that works. Now, of course, in SGX, you can't have something where the OS has full control because now the OS is outside the trust model. You want to restrict what the OS can do. And so the way they did that in SGX1 was to define a very small set of restricted operations as to how you could construct an enclave. In SGX1, basically, the enclave's memory map is totally static once the enclave is constructed. So when the OS is setting up an enclave, it gets to put pages into it using these instructions like EADD, and choose the permissions of each page inside the enclave. And then once the enclave, before the enclave starts executing, it gets finalized. And beyond that point, there are no changes as possible to the enclave's memory map. That's relatively simple, but it's also very limiting. There's no way to dynamically allocate memory inside an enclave, grow a stack, demand load data and code, anything like that is impossible in SGX1. In order to tackle that limitation, SGX2 adds a bunch more instructions for dynamic allocation. So it's now possible for an enclave in SGX2 to dynamically allocate some memory inside the enclave or change the permissions of a page inside the enclave. But even with those 6 instructions, you still don't have the flexibility of a traditional page table. Firstly, we're actually still waiting for the implementation of SGX2. It's actually, I should update this slide, it's something like 3.5 years since Intel published the SGX2 spec, and hardware takes time, so nobody has an implementation of this yet. But secondly, even with those instructions, there's no way to do things that we commonly do in systems, like move a page somewhere else in the address space, or map a page multiple times at different addresses, or share memory between different portions of the address space, or between different enclaves. And so, the natural solution to this is to add yet more instructions to the architecture and wait for another iteration of processor development to get those new instructions to get new functionality. But as you can probably sense, I'm suggesting that this is not a productive path to be on for this kind of complexity to all be baked into the instruction set and into the processor implementation. So the fundamental problem here is that SGX tries to encode something like a mini operating system, something that's sort of tantamount to the complexity of almost a microkernel inside the instruction set. Provide operations for manipulating pages, and we haven't even talked about how SGX represents threads and concurrency, but it has a similar sort of complexity to it. And for good reasons, it's hard and slow to change the architecture, right? The x86 ISA is like the stable point in the stack that gives us backwards compatibility for decades, that allows us to run our software indefinitely forward into the future. So if you want to change the instruction set, first you have to convince Intel that your change is worthwhile. We did that for a few sort of aspects of SGX2 as part of a previous project called Haven, where we ran existing applications inside an enclave. But good luck doing that as an independent researcher. Then you have to wait for Intel to update the spec. Then you have to wait for parts to ship that implement the updated spec. And then, assuming you don't just want to use this in your little research project, assuming you want to run code like, say, in a public cloud, you need to wait for people to buy and deploy enough of these new parts that you can expect to write some software that's going to run on a machine that supports these new features. And that takes a really, really long time. SGX1 is kind of at this point, people are starting to talk about providing enclave enclave mechanisms in the cloud. Azure has announced something that's in private preview. SGX2, we're still at this point, right? We're still waiting for Intel to ship an implementation of SGX2. End-to-end, this total timeline for getting changes into the architecture is something in the order of a decade or more. And that worked when the role between hardware and software was that hardware made software go faster or have more capacity. But it really starts to break when software is fundamentally dependent on hardware changes to enable functionality or to enable security. And that I think is a problem. So, it's not working. And the other minor wrinkle here is that SGX is not going to be the only instance of this. Everybody's realized that this kind of features are compelling. AMD has announced something that is superficially similar, but actually functionally very different from SGX. And I'm sure they won't be the only ones. And so, the worst possible world would be if hardware bifurcates into all these different variations of different complicated secure execution technologies, that software is kind of struggling to deal with this mess.
So can you speculate just a little bit on whether we could also solve this problem by just making microcredit programmable? So thus far I have been talking about hardware in the general sense of the instruction set and everything below it. I think that in some implementations of that, there's a lot more of this complexity that is in microcode that is patchable. And some implementations of it, there's a lot more of it that's in actual gates, right? Like if you buy a RISC-V CPU, there's not a lot of microcode in it. And so definitely getting away from you have to go out and buy a new piece of silicon to get some new feature, and being able to decouple that from silicon evolution would be a hugely valuable thing. But I think that it relies on people like Intel also changing their business model, which is still mostly predicated on you buying a new piece of silicon every 8 years. And that's going to be a hard change for the industry to adopt. Maybe, Intel might not have the incentive to do this, but you could imagine, for example, suppose you were a RISC-V person, and you wanted to have some differentiator with respect to AMD and Intel in a way that gave you more power over time. An example like building block that you might think would be helpful for this would be to say, suppose we could create groups of instructions that could be glommed to, because the issue isn't like that I could go build a part of my microkernel. It's that I have to build a microkernel in the behavior of the system. So if you could, do something where you said, okay, this set of instructions are now going to be executed. This arbitrarily long set of instructions are going to be executed as a unit,
atomically, or with some sort of security guarantee around. But I think, particularly since you mentioned RISC-V, that the risk mindset there is that no, that's software. So, and RISC-V has this thing. RISC-V has this. It has like user mode, supervisor mode, hypervisor, and then it has machine mode, which is just yet another privilege level. And I think that's the riskish answer to that question, which is if you want another place to execute things atomically, then we'll just give you another privilege mode.
Well, except that it's a losing game. I mean, what your argument is kind of it's a losing game. And what's interesting is actually the people who did the original people who did RISC, they were doing programmable microcredit before they did. It was like, that was the big thing before people like swapped back over and do RISC. And now maybe we're actually back to a world where the complexity of the features we want implemented at the hardware level so that you can't get around them. Like that's the thing that's the reason we want this at SGX level.
Yes, because it can't, I mean, it's because it's secure, but then at the same time,
I don't only mean to raise the question.
You raise a whole bunch of valid points. I don't have an answer to it. I think that we're going to, like particularly also with things like Spectre and Meltdown, we're going to have to start acknowledging that the boundary between software and hardware is much more fuzzy than we have traditionally viewed it. I think that's the high-level takeaway. By the way, everybody else should also feel free to interrupt and ask questions. I didn't say that at the beginning, but I'm happy to go with where the questions take me. So this brings us to Komodo. There's my Komodo dragon. the basic idea with Komodo is to get back to a cleaner separation between what's in software and what's in hardware. So the idea with Komodo is let's have simpler hardware primitives on top of which we can build things like enclaves. Move this higher level enclave management stuff, questions about like, what does an enclave virtual address space look like? How do you start executing inside an enclave? How do you manage concurrency inside an enclave? Move that back into software. If we do it right, we can evolve those two independently again, so we're not waiting around for new bits of silicon to get access to some new software functionality. And then the question, of course, is, well, if it's software, why do you trust it? And the answer is because you formally verify the software. And so rather than getting an attestation that says this CPU was manufactured by Intel and here's a public key that backs back to an Intel attestation service or whoever manufactured the CPU, you get an attestation that says here's the hash of the enclave code, the implementation of enclaves on this CPU, and now I can go and look at the formal verification, run the machine check proof of that implementation, and I have arguably a higher basis for trust in the correctness of this thing than purely that the hardware vendor implemented it correctly. So having spent a lot of time banging on SGX, SGX also got a lot of things right, and it's groundbreaking and exciting for a reason. There are a couple of key design features of SGX that we try to preserve with Komodo. The first is if you look at the way SGX was designed, and there's an ePrint paper floating around called SGX Explained that goes into a lot more detail about this. It carefully avoids changes to the processor's fast path. So SGX has this memory encryption engine that's behind the cache that is providing encryption and integrity protection of a region of physical memory that's accessible only to the SGX implementation. All of the enclave management instructions, like the ones I presented that you create and manipulate enclaves with, they're effectively slow path operations, except for the one that goes into and out of an enclave, which we might like to be a bit faster. And all of the core execution resources in the processor, like the cache, the TLB, the instruction engine, all that stuff is effectively unchanged. The other nice feature of SGX is it's largely compatible with existing software. So that means that inside an enclave, you can use basically any x86 instructions. And also the existing system software stack, like the OS and the hypervisor and so on, are largely unmodified to work with SGX.
So do you have a sense of why there's memory encryption engine is so tied to SGX? It's not a separate thing as saying on AMD. Like you cannot just use that one separately.
I don't have a good answer for you for that. I suspect it's partly because they were developed together, and partly because if you're going to do SGX and you have to build the encryption engine, you don't think about how am I going to make the encryption engine accessible to other code. Then you have this complicated trust model of, if I'm letting some other code access the encrypted memory, how does that affect my trust model? I suspect it's probably 90% engineering and maybe 10% product segmentation, marketing decisions. Intel have a white paper, one of these sort of preview specs that they released for comment in the last 6 months for a memory encryption feature that looks not dissimilar to AMD's thing. So you might want to go and look that up. So anyway, the high-level answer to C's question is there's no particularly good reason. And finally, the other thing that SGX does is it delegates resource management to the untrusted OS. So what I mean by that is that all of those SGX instructions that do things like add a page to an enclave or manipulate an enclave's memory map or start executing an enclave or leave an enclave, all of those instructions are things that the system software can do. And so the system software can try to do anything, and SGX implements a bunch of simple rules to prevent things like double mapping of pages or prevent anything that will compromise the security of the enclave. But all of the decisions like the memory allocation policy, the execution policy, all of those kinds of resource management decisions are still in untrusted code. And that helps reduce the complexity of the SGX implementation, but it's also a nice kind of nice kind of way to design the system with a separation of concerns. So in Komodo, we rely on a couple of hardware primitives. The first is some kind of memory isolation mechanism. That could be encryption and integrity protection in the form of SGX. It could be just pure memory encryption like the AMD or the latest Intel spec. Or it could be just some kind of isolated region of memory. And we're kind of ambivalent to this because it really depends on what is your threat model for physical attacks on the machine. It's orthogonal to what does the rest of the software look like. So if you want to have strong security against physical attacks and your memory is off-chip like a regular PC, then you want encryption and probably also integrity protection like SGX. But let's say if you're an embedded system and you have an on-chip RAM that's protected by the physical being inside the same package as the CPU, then maybe you just need memory isolation. Or if physical attacks are out of scope, if you're willing to trust the cloud vendor to protect physical access to their hardware, but you don't want to be compromised by all sorts of software threats, then maybe just regular old RAM with some sort of partitioning mechanism is good enough. The second thing we need is a root of trust for attestation. That's fairly widespread. You have that standard in ThinkMs and a lot of embedded platforms too now. We need a source of randomness to bootstrap public key cryptography to do the attestation with. And what we're really asking for, which is slightly more interesting, is new protection modes in which to run enclaves and a piece of code called the Komodo monitor, which is going to be essentially the security kernel, the security reference monitor for enclaves. If you've done any work with ARM Trust Zone, this picture probably looks quite familiar, and in fact, I'll talk on the next slide about how we build a prototype on top of ARM Trust Zone. But this could also be using things like RISC-V's machine mode, which I mentioned earlier, or it could be using something like hardware virtualization extensions if you don't need to run a hypervisor. Then on top of this, our monitor, which is software, implements a security mechanism. So it's responsible for the code path that allows execution inside an enclave. It's responsible for managing the memory map of an enclave, performing attestation, these kinds of higher level security mechanisms. So instead of SGX, where the instruction set is involved at the level of multiplexing the hardware and protecting all the different enclaves from each other, in Komodo, the hardware provides us one protected execution environment, and we have some trusted privileged software that's doing that multiplexing. So we build a prototype of this on ARM Trust Zone. In ARM Trust Zone, you effectively take your normal user kernel trust model and you bifurcate it. So we have normal world and secure world. And Trust Zone protects secure world from normal world and privileged mode from user mode. So in our Komodo prototype, the monitor runs in secure privileged modes and the enclaves run in secure user mode. And so the Komodo monitor is responsible for protecting enclaves from each other and for protecting enclaves from the actions of all of the code, including the OS on the untrusted side of the machine. The other thing we rely on is having some kind of physical memory that's isolated or encrypted or whatever. A lot of Trust Zone platforms have isolated secure memory. And so then on top of this, we build Komodo as verified assembly code, and it implements two APIs, and it's roughly designed to be comparable to SGX. So you notice it has an interface here to enclaves and another interface to the untrusted OS. So from the point of view of the untrusted OS, it has APIs to do things like create a new address space that's in your enclave, create threads, create page tables, manage the memory mappings inside an enclave. It can measure an enclave. That's part of the attestation mechanism by which you determine the unique secure identity of the enclave. It can execute threads. It can also dynamically allocate memory to the enclave. The enclave gets an API from the monitor that allows it to create and verify attestations, to map and unmap spare pages. That's how you perform dynamic memory allocation, a la SGX2, and to exit the enclave and communicate back to the untrusted world. So this is, not the same API, but roughly comparable to functionality to SGX2. But what's unique here is that it's software, and we provide strong confidence in its correctness using formal verification. So the tools that we're using to do that are a programming language called Daphne, which sits on top of the Z3 SMT solver to do the verification. And the components of our trusted computing base, the portions of the system that we have to verify that manually that they're correct, are a model of the subset of the ARM architecture that we rely on for the implementation. So this models all of the instructions that we use in the implementation. It models the trust zone mechanism of normal world and secure world and the transitions between them, exceptions, interrupts, all of that stuff, but obviously much less than the full instruction set and much less than the full complexity of the hardware. There's actually, incidentally, I should mention, there's been a bunch of work on formalizing the ARM architecture for ARMv8. And so in the future, it would be really nice to look at replacing that model, which we just wrote down and have to make sure we get correct, with something that ties back to the published ARM formal spec. The other part that we have to trust is an abstract spec of correctness for Komodo. So this says, what are the APIs you can call? What do they do to the enclave's memory map? How do they manipulate the enclave state? What are the contents of memory expected to be at certain times? And those two things together specify what is the Komodo implementation supposed to do, but not necessarily the details of how it does it. So then we have the implementation, which is the how it does it part, which is a lot more code that's written in annotated assembly language. And I'll give you an example of that on the next slide, in a language called Veil. Veil is kind of like a higher level language sitting above Daphne that's designed for writing verified assembly code. So Veil takes in this annotated assembly and spits out code, which is basically sequences of assembly instructions in ARM assembly code, and a proof of the correctness of that code. And if these two things are correct, then Daphne checks them against the spec and the ISA model and says, along with some supporting proofs that we have to write by hand in Daphne, says, yep, that's okay. And if it is okay, then we have another trusted small piece of code that turns that into an assembly file that we then hand off to the regular assembler and linker and so forth. So the assembler is in our TCB, and the verification language is in our TCB, but there's nothing high level. Yeah.
Just curious about your experience with Veil, because there's Daphne-based stack is oftentimes very deep, right? You have Boogie, you have Day3, you have Daphne. If you run anything, you cannot verify because of some mistake somewhere. Daphne will say, I don't know how to prove this branch.
Yep.
And you don't know what's going on. And now you are also using Veil on top of Daphne. I'm just curious what the experience was like say, easy or harder, or just to figure out what is going on and how.
There's certainly a learning curve, and it's very steep. I personally, I don't know if it was quick. It was bloody hard. There was a lot of, the x-axis is not necessarily time, but productivity. Let's say that. Okay. I personally don't have a lot of experience with all of the competitors, so I'm the wrong person to answer this question. You do certainly need to know things at the Daphne level of abstraction. You need to have a fairly good model of how Veil is translating things into Daphne. You very, very infrequently need to care about Boogie code. I don't fully understand Boogie. I looked at Boogie sometimes to try to debug a weird error message that was coming out of Z3 when there was a bug in the Daphne code gen and things like that. But I did not have to have a mental model of Boogie to understand what was going on. So, it's hard for me to say this was a good or a bad approach. The project that originated Veil is Everest, which is building the verified, TLS and HTTP stack. They're verifying crypto algorithms, which also use a lot of assembly code for performance, and so that's why they built a tool designed for verifying assembly code. They have now moved to being based on top of F* instead of Daphne, because that gives them some better features for controlling the proof and controlling how the proof goes through. If I was starting this project today, I would probably be building on top of that. There are some ways in which Daphne has lots and lots and lots of high-level language features that we have no need for, and those features don't really get in the way, but they increase the complexity of the proof in that they give lots of stuff to Z3 that Z3 is totally irrelevant to proving the correctness of our code, and so they increase the time it takes to prove things and stuff like that. in addition to that, yeah.
So just kind of a quick question. Maybe this is an artifact of the fact that you use ARM Trustzone. Just curious as to what the suppose if you had different applications which have different enclaves, are they isolated from each other?
Yes.
They are, right? Okay.
Yes.
And the memory isolation of ARM Trustzone is sufficient to.
Yeah. So the way to think about it is that think of orange as everything that's enclavey. The hardware gives us an orange region of physical memory. So it guarantees that nothing in the normal world can access our secure world memory. The monitor partitions the secure world memory so that if you have an enclave and I have an enclave, we never map the same page.
And are there any kind of sort of things related to concurrency with respect to different enclaves executing?
Yes. So what I didn't mention, and the one way in which we have a big simplification for the purposes of verification is that all of this is single core. Because verifying multi-core stuff was just going to be impractical. The implementation complexity of dealing with multi-core and dealing with concurrency inside the monitor is not really that great, because most of the monitor operations are slow path or they don't change state. So like when you go into an enclave, that's local. So we could probably get away with really big locks inside the monitor for the operations that manipulate the memory map. Yeah. But we need to start reasoning about things. Well, even TLB shootdown is not a big deal because on ARM you get this hardware-assisted broadcasts for shootdown, so you don't need to worry about that very much in software either. So in addition to implementing the whole thing in Veil and having a specification, we actually proved some high-level security properties about the specification. And this is really the work of my intern, Andrew Ferriolo, who's the expert on this. But what we did was prove via non-interference an integrity property for enclaves and a confidentiality property for enclaves. And that's a property of the spec. So you get this guarantee that if you have a correct implementation of the spec, then it guarantees that the data inside an enclave cannot be observed, cannot interfere with anything else on the system. That includes other enclaves or the untrusted OS. And those things can't interfere with the execution of the enclave, except through a couple of specific demarcated communication points, interaction points, those being communication across the enclave boundary. So enclaves take register arguments when they're invoked and return results in registers when they return, and they can communicate through explicit insecure shared memory mappings. Exceptions, if you take an interrupt when you're executing inside an enclave, or you take a fault when you're executing inside the enclave, the OS gets told, hey, this enclave took a fault. And the side effects of dynamic allocation. If you ask the OS to allocate a page for you, the OS is going to know that you asked it to allocate a page. It doesn't know where you put it or how often you used it. And yeah.
So Trustzone provides something that's, so maybe you could describe in just a few words what the model of Trustzone is actually intended to provide.
Probably the best way to think about Trustzone is whenever, in a traditional processor, let's say you have a user mode and kernel mode, right? Like a boring old user rings. And kernel mode is always more privileged than user mode. And there's something like a system call to get into kernel mode and then return to user mode. And the kernel mode controls the page tables for user mode, so it can control what user mode has access to, right? So that's the model we're all familiar with. In Trustzone, the one way to think about it would be like, if you took that CPU and you just made a whole other CPU, and that's the secure world. And so secure world also has a kernel mode and a user mode.
So it's like VTX, but not.
But not, because in VTX you get another layer of address translation and you get another layer of privilege below the kernel. Okay. In Trustzone, these two things see the same physical memory map. These things execute in the same physical space. And the hardware sees this memory access came from secure world versus this memory access came from normal world. So you can have something like an IOMMU that partitions off the memory and stops normal world from accessing secure world memory. but it's not another layer of address translation or any of that stuff.
Like a subset of what VTX would be.
Yeah.
Okay. In a weird way. Okay.
Well,
I know. I mean, for what it's for.
if you think about it, it came from like embedded systems where they wanted to have another secure place to do things that was separated off from the OS. It makes a lot of sense. Yeah. So the only thing I was going to say on this slide is the nice thing about this non-interference property is that because we know exactly what we reveal, what we declassify from enclaves, we can say with confidence, for example, that Komodo enclaves are not vulnerable to controlled channel attacks because when an enclave, you learn nothing about page faults inside an enclave, for example. This, of course, doesn't bound anything that is leaked below the level of abstraction of the architecture that we model. So things like cache side channels, speculative execution, all that kind of stuff is out of scope.
And your proofs are with respect to this, to what's running in the trusted zone, right? Like you are using services in the untrusted OS.
We're not using anything in the untrusted OS. The untrusted OS calls into us, and we return results to it. And these non-interference proofs have to have a model of what can the untrusted OS do. So there's a trusted piece of the spec that says the untrusted OS can scribble on any memory outside the enclave, outside the secure world region, for example.
But then otherwise you can ignore it.
Otherwise
you're not actually depending on services.
Correct.
Okay.
Yeah.
And that's in some ways different from Haven?
Yes, totally. Yeah, I mean, Haven was about if you're in this is how you build an enclave. Haven is if you're in an enclave, how do you do useful things inside an enclave with calling out to the OS. Yeah. So to give you a little bit of a flavor of what does this implementation look like, I thought I'd throw some verified assembly code written in Veil and Daphne up on the screen, just to sort of bamboozle you. Think about this times a lot if you want to think about what it's like to implement a system like this. This is a small procedure inside the Veil implementation that is responsible for constructing a second-level page table entry. So this stuff executes when you're mapping a new page to an enclave, for example. And most of the Komodo implementation looks like this. So think of this like a macro assembler language on steroids. This procedure takes a bunch of operands that are abstractions of ARM registers. So this, at call time will be some concrete register. And it has a bunch of preconditions and postconditions. So the preconditions say things like, these registers have to be distinct. You can't pass the same register 3 times. The registers that we're going to modify mustn't alias the stack pointer. One of the arguments has to be page lined. One of the arguments has to correspond to an actual mapping parameter. And it has a bunch of postconditions, which is what do we guarantee to our caller after this procedure runs. So this is very sort of traditional Floyd Horse style verification, pre and post conditions, sequential verification. So after we run, we're going to have constructed a valid PTE, and this is a specification that comes from the ARM machine model that says what is the PTE format supposed to look like. Plus, we're not going to have messed with anything else, right? So we haven't left the machine in a crazy mode. We haven't scribbled on any other registers, all of that stuff. And then inside here, if you squint, you can see some machine instructions. And so those are the things that ultimately end up getting spat out into the .s file that we compile to. And everything else in this procedure is stuff to help the verifier. So there are assertions about the state in between these instructions. And there are things like these guys, which are calls to handwritten Daphne lemmas that also help the verification go through. And this is basically how you build up the implementation of a system of lots of little bits like this, and you glue them all together. So if you think about the whole system is about 21,000 lines of that kind of code. It has to deal with in the implementation. It has to deal with lots of messy, nasty bits of hardware detail, like ARM has all these different machine modes. When you take an exception, you might be in a different mode. You have to switch modes and propagate state across the different modes. You can take interrupts between all these different procedures at various states. There are times when you can't mask out interrupts, so you need to be able to take an interrupt and go off and run some other procedure in the middle of an interrupt. There's this funky register banking feature where, like, when you refer to a register like SP, what you're actually referring to depends upon what mode you're in. All of that kind of nastiness is the stuff that the implementation has to deal with. That's mostly not visible at the abstract spec level. So this is a lot of the stuff that the verification gives us confidence in.
Quick question.
Yeah.
So for the Veil code you showed, that was a very simple piece of code that didn't have any sort of loop or anything
Correct.
like that in there. Why do you need all these assertions? Like I understand that like once there's a lot of complex control flow and like these sorts of things.
Even when you don't have complex control flow, the verification is far from automatic in the sense that it'll just see its way through everything. The assertions, so there are two flavors here. There are these lemma calls, which is hiding a lot of complexity. This lemma proves a lemma that says, if you have this mapping thing, and you bitwise AND it with this constant, and you bitwise XOR it with this other constant, then you end up with a bit in a certain place that's the right bit to put in the page table for the X bit. That's what that lemma call proves for you via calling a series of lower level lemmas about the bitwise operations. Because one thing that we struggled with was that the interface between integer operations and bitwise operations is very flaky in Z3 proofs. So particularly things that's doing bit shifting needs a lot of help. The assertions are largely there to cut down the proof time from exploding. And so these things say to the verifier, when you're in this state, this register is either 0 or this flag. And if it's 0, it means that this abstract state was the state that you're in. This effectively, this is something that's really obvious that I know, but by writing it down, I help constrain the search space for Z3. And that allows me to put more of these instructions into one procedure. If I didn't want to have all these assertions, I'd have to have much, much smaller procedures. And then the glue between all the procedures, writing all the pre and post conditions, gets really nasty. So we built a prototype of this, and it runs on a Raspberry Pi 2. This, I was just saying at lunch, in hindsight, this was probably one of the worst decisions I made in this project. The Raspberry Pi is a readily available, easy to acquire TrustZone platform. It does not actually have any security. So what that means is that the untrusted OS can at any point in time read and scribble on our secure world memory. So although the implementation is the same, the proof is the same, the performance is the same, there's no practical security isolation. That's not why it was a bad decision. It was a bad decision because the interrupt controller on this thing is not TrustZone aware either. And so we actually had to do a bunch of extra work in the implementation and in the proof to deal with things like interrupts coming into secure world that then need to be reflected back into normal world. In order to enable that, we build a bunch of other stuff like a bootloader that runs this thing and then boots Linux in the normal world. None of that boot code is verified, but it could be. It's actually much simpler than the Komodo monitor because it doesn't take any exceptions, doesn't take interrupts. It's just straight line code that's setting a whole lot of architectural state. And we also built an untrusted driver that runs in the normal OS to interact with this thing and allow you to create enclaves and manage them. We did a little bit of performance evaluation on this. The high-level result here is that entering and exiting an enclave. So this is you're in an application in the normal OS. You want to call into an enclave and then return back to the normal OS. Takes around 700 cycles, and that compares very favorably. In fact, it's an order of magnitude better to the equivalent operation on SGX, where it's about 7,000 cycles in the first implementation. Now, I don't want to really brag too much about this because it's a very apples and oranges comparison. The ARMv7 in the Raspberry Pi is a very, very much simpler processor than a modern Intel CPU. Besides the clock rate difference, it also has a simple in-order pipeline, so it's much faster to do things like switch protection. But at the same time, it does sort of give you some confidence that there's certainly no inherent performance penalty from doing this kind of stuff in software than in hardware.
Hardware that's implemented at the instruction level that takes 7,000 cycles. And that you're going to trust this.
Yeah, I mean, of the 7,000 cycles is not necessarily all going to execution. It's going to flushing TLBs and things like that as well. But yeah, certainly there's a lot of code executing there that's doing something.
Like, in your API, right, Komodo's API, you have those SMC calls to construct the page table. Whereas in SGX, they just cannot trust anything from the page table, so they have to flush the table entirely.
That's true. So we do get one. There's one sort of benefit here, which is that on ARM implementations, the TLBs are tagged to say that's a secure world TLB entry or a normal world TLB entry. I don't know what the story is for the Raspberry. I think it's a property, well, because it's inside the core, so it's independent of the board that you're on. And so we don't have to flush the TLB if we were not lazy in our implementation for reasons of verification expedience. We actually do flush the TLB. So this is one of these things that we could optimize and verify, and then this number would get even better. And so, yeah, I just said that point. There's plenty of scope for optimizing that number. We also did a higher level sort of performance. We built a notary enclave, which is one of the applications from the Iron Fleet work, and we ran that in Komodo. And this graph is totally uninteresting. It shows you that executing the same user mode instructions that are doing public key crypto in an enclave in secure world is exactly as fast as executing them in a process in user mode. Which is not surprising.
Just curious how different it is from the original Ironclad notary app. I remember that one is doing the RSA sign on a counter. Right?
This is doing exactly that same thing. We rebuilt it. We rebuilt it just in unverified C code, so it's not trying to use the Ironclad implementation, but it's doing the same crypto operations. And so, yeah, because it's doing RSA, it spends all its time in user mode anyway, so it's not interesting. Perhaps more interesting is the verification effort. We spent, as a team, about 2 person years on this project for, 4,500 lines of trusted spec to 18,500 lines of proof, which, from what I'm told, is roughly in the ballpark for these kinds of projects. That 4,000 lines of spec is our TCB along with our verification tool stack. But remember I mentioned that we have these high-level security proofs of non-interference properties. That's only, the spec for that is expressed in only a couple of hundred lines of code. So that actually gives us a high degree of confidence in the correctness of our spec.
I think you said before that you get about 10,000 lines of implementation. Isn't that?
No, I said 20,000. When the number I gave before was like 20,000 lines of code. That's these two put together. So this is in this count we're decoupling actual ARM instructions and like control flow stuff from all of the annotations to make the proof go through.
So the Komodo.s file is.
The Komodo.s the Komodo.s file is huge. The reason it's huge is because we inline all the procedure calls. This is another sort of prototype cut corners thing. And where that really blows up is for SHA, because we use SHA to do our attestation. There's a couple of calls for SHA and they all get inlined and expanded. So the Komodo.s file is like 30,000 lines of assembly or something disgusting. If we implemented a function call and return, that would get down to a reasonable number. So I'll talk briefly about experiences and related work and so forth, but since we only have a few minutes left, I'm also happy to just spend the time taking questions. One experience was that verification is effective at finding bugs. When we started on this project, I built a first prototype in C and assembly just to sort of exercise all the different bits of trust zone and make sure that this thing was going to work. And that was only a few hundred lines of C. And it was very, very simple code. It didn't implement any of the attestation. And yet it had really dumb, in hindsight, glaringly obvious bugs that only showed up as a side effect of doing the specification and the implementation. Things like checking that 2 parameters were both pointing to valid pages, but I never thought to check that they were not pointing to the same page, right? And it was only like trying to debug why I couldn't prove a consistency property about the spec that this bug came to light. The other one is, agreeing with Pedro's experience with looking at verified distributed systems. That even when we finished this, there were still bugs in the parts of the system that we didn't specify. So I spent quite a while chasing down niggly details of the ARM cache coherence semantics between secure world and normal world, which is related to how the bootloader was setting up page tables. There was a liveness bug where if you took an interrupt at the wrong time, it wouldn't compromise the security of the system, but it would also put you in an unrecoverable state, and you had to reboot to get out of the state. Stuff like this. There's always going to be some kind of part of the system that is outside the scope of what you're verifying, and so the goal should be to get that as small as possible. And the tools are improving, but they still have limits. So I talked about this a little bit in the answer to Z's question. Timeouts and proof stability are a particular challenge with our tool stack. I found myself writing what I would regard as very inelegant code, breaking things up into tiny, tiny procedures with explicit pre and post conditions and lots of assertions in order to get the proofs to go through. So there was a definite trade-off between clarity and verification, which feels counterproductive. In terms of related work, I'll just do this slide super quickly. I'll say the high-level takeaway from this slide is there's a bunch of work on enclave-like systems, and our main novelty there is a verified implementation and something that works on ARM Trust Zone. And there's a whole bunch of work on verification, verified kernels, and the real distinction there is because we're implementing just enclaves, our system is quite a bit simpler than a verified OS in some important respects, like it doesn't handle interrupts or scheduled threads. And we also have to verify things like our attestation mechanism and the non-interference properties.
So, have you thought about doing even simpler execution model? I mean, an example would be like an SFI-like system or something. Like one could imagine you could build some kind of verification system for entering and exiting a process, for example.
Sure, I understood the question.
Well, so an example would be like, one could imagine building SFI being an example of a software implementation of what is a hardware, which you can actually just directly implement in hardware if you decide you don't want to do that.
But SFI, maybe I'm picking up on the example and getting misdirected. SFI gives you a very limited security property, which is just about
non-exit. But I mean, it would be other aspects of that behavior of the exit.
Whether we could move some of the complexity into runtime checks and have to save having to verify everything.
Possibly, I'm going in the direction of trying to understand, like one could potentially take this type of approach and use it for other types of kind of limited execution environments that are done in software as part of an operating system service. And Enclaves is an example of an operating system service that I can now provide this way in software and not have to wait for the hardware for it. And I can imagine similarly, I could think of, I have an operating system service which is like a lightweight process that has certain exit points or entry points, and I'll validate.
Yes, okay. Coming from the perspective of we have this big legacy complicated operating system, how can we provide cut out pieces of it and improve the confidence in those pieces incrementally? That's an interesting idea. I haven't thought about it in any depth, but I'd wager there are other aspects of the system that you could do that too. Like I know people have worked on like verified bytecode interpreters and things like that, right? That's another example of that kind of thing. Yeah. Two big things I'd like to do in the future with a system like this. The first one, which is really one that we just cut for time, is having some way to upcall into the enclave to say you took a fault, because I really believe that's the right way to do paging and to deal with dynamic paging of enclaves, is to push that into LibraryOS type functionality inside the enclave. The other one, and the biggest limitation on the practical deployability of something like Komodo right now, and in my view, the biggest limitation of a lot of the verification technology is multiprocessor support. And that's a sort of big open challenge for software verification, notwithstanding systems like Certicos that have done a lot of work in that space. The nice thing I mentioned at the beginning is that for something as simple as Komodo, you could probably get away with 1 or 2 really big blocks. So to wrap up,
Sorry, can I ask
yeah.
one more question before you wrap up?
Yeah.
So the other aspect that you might think that this would be valuable for would be rapid prototyping of the interface that you are implementing in hardware. And I don't know if you've thought about things that you maybe would do differently in SGX2 or SGX3 that you hadn't before, or is it just that you were implementing something that was modeled essentially after SGX2?
in this case, it was very much modeled after SGX because we wanted to be able to make a claim of comparable functionality. Yeah, it's an interesting. I mean, if you wanted to do rapid prototyping, you certainly wouldn't be doing it with a verified software. You would just be doing it with software.
Nevertheless,
you'd like to be able to show that
you hadn't done something wrong.
Yes, right. So this is, I view this as a kind of middle ground between just writing some code and waiting for it to be inevitably baked into hardware in terms of how much time it takes. And it also, I think, gives you much higher confidence in correctness than baking it into hardware. Yeah. So SGX implements enclaves entirely as an instruction set feature. Our goal with Komodo is to really get away from that and decouple simpler hardware primitives from software that can tackle a lot of these high-level abstractions and complexity. We've proven high-level security properties of our implementation, like confidentiality and integrity. And I didn't mention this before, but we've also demonstrated evolvability. So between, like this was an SOSP paper, between the submitted version of the paper and the camera ready, we added all the dynamic memory allocation features in about 6 months. And you can go and look at all our lovely, ugly, verified assembly code on GitHub. So that's it. I'm happy to take any last questions if anybody has them.
So it seemed like the story for attestation was pretty similar to SGX. Is that fair, or is that?
It's conceptually similar. It's a much simpler mechanism. So our attestation is really just a MAC of the enclave's measurement, which is itself a SHA hash of enclave pages, and an enclave supplied secret and a platform secret. In SGX, they added a fair amount more complexity to the attestation mechanism. So you can have things like security version numbers. You can go forwards but not backwards in security version numbers. They have a level of indirection where somebody signs the enclave and then the attestation is indirected from that. This was a sort of thing of what gives us a strong security guarantee that's also the simplest thing we can implement and verify. It's meant to be equivalent in terms of security, but not necessarily in terms of functionality to the SGX attestation mechanism.
Okay, and conceptually, is that like the best we can hope for in terms of an attestation mechanism that's strong and also simple? Or do you see room for further improvement?
I mean, I haven't thought too much about how to do the attestation. We can certainly do better. It's a question of how much verified assembly code for crypto do you want to write? And so, when people like Everest start providing verified implementations of public key algorithms and things like that, we can leverage it. It's kind of, for me, attestation is something you have to have a useful enclave. But it's orthogonal to all of these really nitty-gritty questions like how do you manage memory and threads and all this kind of stuff inside the enclave. That was more the hard sort of design question in Komodo.
The Komodo API is a much simplified version of Intel SGX. So there is a gap between the Intel SGX API and the Komodo API. So in terms of application programmability, is there any difference? Is there any Intel SGX application that cannot be implemented atop Komodo? Or
I'm not sure why you say there's a gap. I think that the only gap in terms of functionality that I'm aware of is that when a Komodo enclave takes any kind of exception, that thread is effectively dead. In the sense that that thread exits, all of its intermediate state gets lost. You could do something to destroy the thread and create a new one and keep going, but you can't handle the exception inside the enclave. Whereas in SGX, there's this mechanism for pushing the context on an exception stack, and then code inside the enclave can actually handle that exception and recover. And that's what I mentioned in future work as the main thing I'd like to add to a Komodo-like system. I don't think there's any other significant functionality gaps. The other thing, oh, sorry, I should say no. Let me walk back from that. The other big thing that SGX has is sealing for persistent storage and support for paging. So when you have a limited amount of encrypted memory, SGX will have these instructions that allow you to encrypt that memory and page it to backing store. Komodo doesn't implement that because, my perspective on that is it should be something that's done inside the enclave. I don't know if that answered the question. Yeah.
More details on the instrument. When you guys start to add dynamic memory to it, I don't know how much is a change for the verification part, because before you had, if you imagine the actors, like things would issue calls to your reference monitor would be mostly non-trusted OS.
Yep.
Once you add this augment stuff thing, and
We
endpoints will do that too. So non-trusted proofs.
There were some significant structural changes. So we already had calls from the enclave because the enclave could exit and it could create and verify attestations. That was already there. But what changed is that there's this abstraction of enclave state called the page DB, which says, like, what is every enclave address space? What is the use of all the secure memory in the system? That previously had only ever changed in response to calls from the OS. It had not changed in response to calls for the enclave. So we had to do a non-trivial amount of refactoring in our spec to admit page DB changes as a result of enclave execution. That was probably the hairiest part of that change. Yeah. We did it. It wasn't easy. It wasn't impossible. I mean, I will say that refactoring verified code is something you have to think much more about strategically than refactoring unverified code. There's a much bigger cost to getting the wrong abstractions in place with verified code. I will definitely say that. Refactoring the spec was not nearly as bad as refactoring parts of the implementation. So, like, one of the things I did in order to allow, I don't know if we're running over, if we need to wrap up, I can just keep talking to Z. One of the things we did in order to allow, like, dynamic allocation from the enclave was I refactored some of the implementation of the memory management code, like the things that's constructing and manipulating page tables, to have flexible register allocation and to be callable from either context. So it can be called from the context where you're handling an OS SMC or you're handling an enclave system call. And refactoring all those code paths to use arbitrary registers instead of hard-coded register allocation, and to weaken the pre and post conditions on all the interactions between those things. That was a lot more work than the change you were asking about to the spec. Just getting all those proofs to go through again.